Right, thank you, Jing. And first, my apologies. Of course, the system has a name, it's MicroFS. I apologize, I should know better. So we have, let's see, one question coming in live from Sturgis, promoting Sturgis to panelist. Sturgis, go ahead.
Hi, this is Stelios Anastasiadis from the University of Ioannina in Greece. This is interesting work. I have a couple of questions. The first one is about POSIX. So my understanding is that the file descriptors of each client are assigned by the server, by the use server. And the question is, how do we achieve compatibility with the standard Unix model in which each client process has its own private file descriptor table? For example, what do you do with fork or with dupe and so on? Thank you.
Yeah, that's a great question for compatibility. I guess we still have the, because our file system still maintain the single file descriptor for one process by ourselves. And we ensure there's not duplicate file descriptor for different files. And we don't solve the problem, we don't have a very good solution for the file descriptor compatibility with the host file system. For example, you access to normal exe file, we just ensure the file descriptor is pretty large, and we check that carefully in the library part. But for fork, the library need to redirect the fork, and the kernel need to redirect the request to our file systems to solve that issue. Currently, this feature is need to be implemented, I guess. Yeah.
Thank you. I have one more question, if I have some time.
Go ahead.
Thank you. So the second question is about scalability. So how performance and scalability are affected by managing all the directories with a single primary thread, or by using leases for caching at the client side? Because I saw both these techniques are used in the design of the system.
Yeah, I think this is a very reasonable concern. In the paper, we have the micro benchmark to evaluate all the server directory operations. The micro benchmark means you have, for example, tens of applications just crazily issue make directory. And the result is we're pretty comparable with the kernel file system. Because the complexity of the, for rename and make directory, usually it's going to lock the whole directory. For kernel file systems simplicity, it's just still a lot of bugs here. So this is kind of the reason that we get reasonable comparable performance in micro benchmark. Yes, but another point we want to make clear is why we believe this is a reasonable assumption is we think the frequency, stressing the make directory in a very, very short frequency is not going to be very common in common workload. For example, you have server data operations and then you have directory operation like that. So we think it's going to be reasonable in the real app, more realistic workloads. This is kind of the assumption we take.
Okay, thank you very much.
Thank you both. And the next question is by Xudong.
Oh, yeah. So my question is that because UFS is a semi-microkernel approach, so the nature here is that even if UFS crashes, the kernel doesn't crash. And I think there should be a chance that you can actually restart UFS. So this is basically something you can leverage to achieve higher reliability. And my question is that do the user application need to be modified to leverage it, or is actually transparent?
You mean I think you're talking about a very good opportunity for UFS, such that it has a better potential for reliability in the sense that it can transparently survive instead of a kernel panic.
Right.
It's good to I think this is we don't like we can reboot the file system now, and but we don't have a very good. I mean, this is kind of the part of the future work.
Yeah.
I guess we don't have a very good solution for now because you need to really, for file system, the complex really is the state. Like we need to guarantee the state is correctly recovered. Like the one single approach is let's just restart everything. That's the simplest way, which also works with kernel rebooting. I think we are pretty close to that state, such that, for example, some files, some request is just simply cached, and we just clean everything and replay the request. This is will enable some transparent recovery, but that's a very excellent question. Thank you.
Okay, thank you. I think it's a quite interesting direction. Thank you.
Thank you. Maybe to follow on to just generalize that question a little bit, you call MicroFS a semi-microkernel. How much weight do we have to give to that distinction between microkernel and semi-microkernel? Why did you go with calling it specifically a semi-microkernel? What's different to a microkernel file system?
Yeah, I guess I'm very grateful you asked this question because we kind of like the term in the sense that like the Google's network and you know your work of TAS does this. It's kind of different in the sense that the microkernel is like everything is a process. And everything is inter-process communication. And there's a long debate of whether it's a good idea, its performance is bad, its modularity. And it's just, so we just borrow this idea for sure, but I think the intuition is IO, including the networking IO and the file storage IO is pretty, it's important, it's complex, and it's worthwhile to spend a lot of engineering effort and the research thoughts to make it efficient and easy to deploy in the data center. And also over the years we built a system and we know how to make it better to work with modern devices. So we call it semi, like share the spirit that we want to keep it compatible with the kernel, because you know, it's just very, very hard to get rid of the kernel entirely. This is kind of the reason that like Linux is everywhere and we don't want to give it up, but we think the opportunity is something like we have very dedicated IO processing in as of microkernel, so we call it semi-microkernel.
Mm-hmm. So you take a very strict view of microkernel. Jochen Lieke would be proud.
Okay, thanks for the talk. And okay, Jing is ready to take the questions. So let's kick off with a question in our Slack channel. It's Erin Zhang from Microsoft Research. She asked, if you didn't have to support the POSIX interface, what would you change?
Firstly, I think I would change I guess I would change the file descriptor. For example, give a simple example, I will have something like open close, like open read, open plus read, open plus read close, like that, instead of every time I open a file, like you open a file, you create a file, and then you return a file descriptor. But sometimes you create a file just simply for create, you don't want to close it. Like the decouple the creation of a file and use get a handle to access the file is quite different. I guess this is one point. I guess another point I want to talk about is kind of especially for the asynchronous and synchronous point. I guess that's the most interesting point to change. Like, especially for networking IO, I guess this is asynchronous trained. And I would say IO is particularly towards that trend, but we really don't know how to do the asynchronous part. I guess I would happy to do that part, explorations through our work.
Oh, thank you. So another question in our Slack channel is from Jing from SGTU, and he asked, is it zero copy to do read and write? And how do you reduce the data copy in UFS?
I wouldn't say it's really zero copy per se, as in some work. I mean, some work, zero copy is literally, they can do the copy from your L2 cache to the NIC. For me, that's the real zero copy. But for us, our approach is called Semi-Microkernel, in the sense that we still, when you access a device, you must go through the file system microkernel. That is, we are not allow application to directly read and write device, at least at this moment. So at least there is need one copy. We pay that for a simple schema because you don't need to handle change the permission, how you access the hardware, because otherwise you need to manage the permission. I guess, but we have the technique to reduce copy for that. We have a memory allocator like interface. For example, when you call read, you can call our malloc, and then the page is actually shared through the server, such that you reduce the copy for that. I guess that's one technique we use.
Okay, thank you. So June Park, you can answer your question now.
Oh, hello. It's a really good research, I guess, and interesting. I want to ask two questions. It seems like the performance of sequential.
Sorry, by the way, are you going to show the video or?
What?
Are you going to? I cannot see the video.
Yeah.
Okay.
Sorry.
Yeah.
It seems like the performance of sequential writes gets more benefit than other operations. Do you know the reason? According to the experiments you showed in the presentation, it seems like the sequential shows more benefits than other operations. So do you have any other reason?
Presentation one?
Yeah. The
yeah.
YCSB sequential gets more benefit.
Yeah, I guess that's the particular case that really dedicated to one, like for that work, I guess level DB is log structure merge tree, and for the sequential load is like it's kind of bounded by the journal part, and we have good device access and high scalable journal design, such that when you really bonded, the file system is bonded to the journal transaction part. We are very good at that. So you can see the experiment result in the micro benchmark. And that workload is exactly bounded by that. So we get pretty good neat result for that. So, and then because it's kind of a pure workload, so we see a lot of improvement. And other part is like other workloads is kind of mixture, and we like it's more complex, I guess, because lower DB has, you know, compaction, kind of like that stuff. It's kind of like that, yeah.
That makes sense. And with high performance IO devices, many studies try to bypass kernel or minimize the kernel intervention. Do you think this is the future, like the Linux kernel should be modified like that, in that way?
I think IO is a positive like attempt for that. And I also see, like, I think in last OSDI, they're pretty neat work about how to collocate several interrupt and adaptive pooling. I guess both of the, like, people in the kernel work, they're trying, because, you know, as I said earlier, kernel is like, it's not going to gone. It's going to be there to support all of application. I don't quite have a very good intuition of how kernel is going to be like, because the kernel words is more complex, like deploying one feature and propose one feature takes a lot of discussion. And I think research people is going to put some efforts for that to improve, to keep improving that, including some more things like hardware co-design. This is my understanding. And I think we choose to take another approach, like this kind of, I guess for higher performance IO devices, it's just, we like to try like another approach that's different than the kernel, because there's a lot of legacy, which is very hard to change in that stack, I guess.
Thank you for the great talk.
Thank you for the question.
Okay, thank you.